You see here in the rack mounts, we have the different equipment belonging to the second demonstration of Metro Hall project, where we are going to showcase the benefits of network slicing for improving public safety. In the demo, we have a Metro network comprises of 3 micro-ROADMs. 2 of the micro-ROADMs are located here, the other one is located. Then the micro-ROADMs, we have 2 optical transponders, which create an end-to-end optical light path connectivity. The 2 transponders are connected to 2 Mellanox switches, where actually the traffic are going to go toward the optical layer. The 2 Mellanox switches are also connected to compute nodes. The 2 compute nodes are these 2 which host the OpenStack instances where we run the virtual machines. The virtual machines that host the Cayuga video management system of our demonstration. In addition to these pieces, we also have the numbit probe, which is an active probe to measure the end-to-end latency of the connections. These are the compute layer and the connectivity layer. We have 3 cameras, 1 fixed camera, 1 PTZ camera, and 1 thermal camera, which are hosted in the surveillance zone on the rooftop of HHI. The cameras are connected to these equipment through a multi-mode fiber, so we have them hosted in the rooftop. The different parts of the video management system, including the video analytics, are hosted on the LANer servers, where the computing takes place and the output of the video analytics return back to the video cameras. We have a 41-kilometer fiber spool that is currently connected. We also have 80-kilometer fiber spools where we exchange them to measure different latencies that is affected by the length of the fiber that is used for interconnecting the nodes.
So the role of Net2Plan is divided into main tasks. First, trigger the demonstration by instantiating the multi-site network service, and second, provide optimality by executing a resolve algorithm. When clicking on the load button, Net2Plan loads first the graph of the existing topology in terms of nodes and links to create the network topology. Second, the list of available network service descriptors to create in OSM. And finally, the compute resources available in the 2 OpenStack virtual infrastructure manager. Additionally, in the background, the network service descriptor of the demo is being uploaded after the load phase. Then the corresponding network service is selected from the graphic user interface. Okay, I'm already selecting them. And its features will be used as an input of the algorithm. Moreover, additional parameters must be set to be used as an input, such as the origin and the destination nodes, the emulated bandwidth, that I am already setting, and the latency limit. Once all is set, we click on Run to start the execution of the algorithm. When the algorithm ends, the shortest path in the topology and the location of the VNFs to be deployed in the corresponding bin are returned. With this output, Net2Plan builds a concrete HTTP request to command OSM in how to instantiate the network service in the system.
So we have the network service getting ready like before. I have in parallel, I have the log here for the OSM. So the WAN connectivity has been deployed from the parent controller. So let's see here, the OSM is active, and let's go to the OpenStack. So the VNF is active, the VNF is up. The other VNF on the other OpenStack is also up. And let's go to ONOS now. Let's go to the intents. So we have one intent installed, the other is installing. It will be installed momentarily. Let's go to the flows. So in the OLS, the flows are added, both of them. Let's go to the transponders. So 2 flows are added, 2 are pending added. They will be installed momentarily. Let's go to the other one. So again, they will be installed momentarily. So they are all okay. So now they are installed. So let's go to the intents. Okay, so intent will be installed, but at the device level, it's already done.
Okay, so from the perspective of the quad flexes, we see that, for example, quad flex 1, we have an OT100 channel created associated to one of the client ports. On the monitor side, we can see that it's transmitting 1.1 dBms and it's receiving minus 12 dBms. So from the perspective of the quad flexes, both are transmitting and receiving power. And from the perspective of the OLS, we can see here, I don't know if the font is too small, but we can see on the ensemble controller that there is a light path established between the ROADM 1 and the ROADM 2. The administrative state is up, and the operational status is also up. That means there is a laser is being transmitting on that particular channel. So everything is up and running.
So once the connectivity has been established, the parent controller has sent the information through an automatic interface to the MDA controller, and in the MDA controller we can see the topology that has been deployed. We have the two ROAMs with the with the two transponders, the switches, and we have also two active proofs connected to the switches. So now, well, we can also see the topology that. So good. So we were here in the topology. So this is the graphical view of the topology. We can also go to the topology. Here we can see the different nodes, also the IPs of the nodes. In particular, the IPs of the proofs are here. We can see also the connections that have been established. We have a optical connectivity and also a point-to-point connectivity in layer 2. So now we can run the application that connects to the proofs and ask them to measure the layer 2 connectivity to obtain the we select the right VPN to measure the throughput and the latency. We have two different modes. We can measure, verify the throughput, and with a course measure the latency, or the opposite. We are going to use this because it's a point-to-point connection. Is going to work well, I hope. So if we execute this script, the MDA controller is contacting the proofs through an automatic interface that we have implemented. The proof are measuring the connection, and the measure has finished. We can see here the results. So these are the parameters that were configured for this test, and we have here the results. So we can see that the throughput is 1.7 gigabit per second. And the latency is about it's 429 microseconds with very low jitter and zero packet losses. And that's all from for the measurements. Yeah, we can see also the other one, but in this case the is not going to see very differences in the delay, but the throughput is not going to be very well measured here, because so now after the new connection has been established, let us launch again the measurement. So we select the same. I'm going to repeat both tests with throughput fine and latency course and the vice versa. So let us execute this first. This is finished. So now we have in this measurement we have the same throughput, basically 97 gigabit per second, and the latency now is double because of the length of the circuit. So if we run with the other configuration, now throughput course latency fine. Let us see if there is some difference now. So I'm going to refresh, now finish, and yeah, basically the same measure, 800 microseconds.
Okay, so here is the surveillance zone of the demo. So here we are at the rooftop of HHI where we set up these three cameras. The PTZ cameras that is used for tracking the object, the thermal camera which is located in the middle, and the fixed camera which is used for intrusion detection. So in this area, as we saw in the other shots, once an object is moving around, in this case it's a person, the thermal camera is actually recording that movement and send a notification for the PTZ camera that tracks the object. In addition to that, the fixed camera sends the streams to the video analytics engine that runs on one of the virtual machines. It tracks and detects once the person is actually going to a very extreme edge, which we have identified these as zones. If you cross it, it will return an alert that a zone crossing has been detected. So that part of the analytics runs on the virtual machines, and the tracking runs on the camera itself.
Here on the left side is a thermal camera, and this thermal camera detects objects in this area here, which is drawn with this white rectangle or a polygon here. And on the left side, we have a PTZ camera, and the target is now that the PTZ camera follows an object which has been detected from this thermal camera. So now Mike was detected from the thermal camera, and now the PTZ camera starts zooming in and moving to the object. And yeah, then as long as Mike is in the screen of the thermal camera, the PTZ camera will follow this object.
So maybe now, Mike, you can go to the extreme edge that we also see that the intrusion detection, because the alerts can be seen on the right-hand side. So I see the alerts maybe, so now the only alert at the moment is thermal. Okay, now the other one is also activated. So it's like
Yes.
6 camera zone.
Yeah. So now we have two alerts, as mentioned by Benam. One is for the thermal tracking, and the second one is for the zone crossing. And the zone crossing analytics algorithm then is a server-based analytics algorithm.
So I think in addition to that, I have a controller here in the office, so I can remotely from the client PC move around the PTZ cameras. So now the PTZ camera is actually, if Mike goes out of the scene, I mean, even in that case, if he stays somewhere, I can take over the control of the PTZ camera and walk around and move it around to see something. So I will do that right in a moment. Okay. So now you see, so the weather today in Berlin is quite nice. So it's sunny, and now I can walk around with the PTZ camera across the rooftop and see what is there. So it's like, yeah. So we also have this option of remote controlling it. So Mike is there shaking hands.